Hi, it's Terry Denery of the MathWorks. So in this video, we're going to talk about this equation generator for the mechanical system dynamics, right? And so you're looking at MathWorks website, and it's a posting for this tool called MotionGenesis Kane. It's part of our MathWorks Connections program. And I really I think it's very appropriate that Kane's name is showing up in here. And so the tool and the company that creates MotionGenesis, mostly led by a very good friend of mine named Paul Mittagey. And Paul Mittagey and I both did our PhDs at Stanford in the 1990s. And so Paul's advisor was Professor Thomas Kane. All right. And anyways, you might say, well, certainly, Kane has been very involved in the creation of this thing called MotionGenesis, which is a symbolic manipulator that generates these systems of equations. But Paul, being one of his graduate students, has absolutely kind of developed this to be this very, very useful tool. And so anyways, you might say it's a tribute to kind of the legacy of Kane as the person who really, throughout, I'd say the 1960s and 70s, really developed this methodology for employing analysis that gets you a very, I'll say, numerically efficiently solved representation of the dynamics of complex mechanical systems, right? And so that's kind of what Kane is. MotionGenesis, Kane is all about. And so, anyways, my good buddy Paul Mittagey has created this company that does this, has a website right here, and lots of useful stuff here, including lots of books that can help you come up to speed on the methods as well as the tool. And I also like that Paul puts this MathWorks partner emblem right up front on the top of his website, indicating how, among other things, how important it is to him to have a tool that works so well with MathWorks, MATLAB, and Simulink. So, anyways, without further ado, let's get into this demonstration. All right, and it's going to begin with SimWise. All right, so SimWise we've shown in previous videos, and a great tool for modeling mechanical systems. It's a mechanical simulation tool itself. I'll remind you of that by just simply hitting the run button. But it's really about its ability to capture a mechanical description through very efficient model building processes. The employs what are our terms for it. Drag and click kind of user interface. So anyways, let's kind of get into this piece of it. All right, and this basically, there's that model. It's in this directory. The directory is called Small Four-Bar Mechanics, Rev November 11th, 2020. So that's the day, you can kind of see right there, that I'm recording this video. All right, so let's now get to the importation of that mechanical model. I'm going to show you the function and really kind of the overall, I'll call it, platform for importing geometry, which begins with essentially getGeometry. And getGeometry calls this function, which is connect to SimWise and build the mechanics model, very early, and most of what happens takes place in this function. That's the main, I'll call, driver of the overall algorithm. And you'll see I put in some breakpoints, meaning the MATLAB calculation will stop when it gets to this line. And so it's going to have breakpoints when essentially a MotionGenesis input deck is going to be created, and then it's going to have a breakpoint right before the Simulink model that employs SimScape multibody is implemented. So anyways, let's go ahead and run this. And so I'll just double click getGeometry, and 1, 1 is a parameterization that I've pretty much been using throughout. Okay, and so at this point it's kind of gotten through quite a bit, right? But it's kind of stopped at this command. And I'll just kind of show you that it's gathered all the information that essentially describes the mechanism in that SimWise file right here. And you'll see assemblies and bodies and frames and joints and all kinds of stuff. All right. Now, actually, before I let it run that next step, I want to just kind of show you this is where we stand, right? So we did simply have the small 4-bar Simwise file, but you'll see the script has already added the STL files, and it's also added an important Simulink block library. Right. Okay, so now let's get back in the right directory. So it's got access to the various functions that it needs to run to continue calculation, right? And so I'm gonna let it run just one line. So I'll step through this next command line. And so it just ran that command, and I'll show you what that directory looks like again now, right? And you'll see that it went through and it wrote these text files, and these are essentially inputs that we can use with the tool MotionGenesis, right? And so let's get back to the sandbox, and let's let the run continue, and it brings us to the function that's going to command the building the sim mechanics model. And actually, here's an important point. All right, so here's this function that's essentially going to create a Simulink model and then load it up with all the blocks that are needed to represent this mechanism, and it will populate all the data fields of those blocks so that it truly accurately represents the system. And so we're sending in all kinds of information. You'll see these data structures, and there are 3 bodies, and that's why simple reps is used here. Now, simple reps is a term that we brought into this to account for some important things that we might get into in further videos. But I'll say it's in general the means of bringing in a group of bodies or parts that will not move relative to each other and allows an introduction of a simplification, which would be to represent them with one simple representation, right? And so it's a good term. It's a term that I in part borrowed from Pro Engineer, who uses this same kind of idea in the various things that they do with Pro Engineer, right? And so my only point right now, though, is that I'm sending in essentially the description of the mechanism through all these data structures, and that's very much what we did to generate the input decks for MotionGenesis, and hence a consistency of the mechanical design or its definition through these data structures. All right, so anyways, again, without further ado, I'm liking that word or that term right now. Let's continue. And as we continue, we should see it launch a Simulink model, which we just did, and it's going to start populating it with the blocks that are going to describe the mechanism that we formed inside Simwise. Okay, and so there we go is the model. Let's hit run. And again, just do these, important validations and make sure we got what we think we got, which we do. Okay, so now let's get into MotionGenesis, right? And so here's MotionGenesis. This is my buddy Paul Medege's baby. He's the main creator of this, and I essentially created an application that works, on Windows. Okay, now I want to get to those input decks. So I'll go back to this directory. We see them all right there. Okay, and this is a default creation, but essentially was written by my MATLAB application called Get Geometry. And I think I'll just kind of run it in its initial format right now. Okay, and actually I want to show one thing before I run this, is that the program is going to finish by writing this file mg small 4 bar into this directory. So anyways, let's bring MotionGenesis up, and let's just paste in all that stuff I just copied into it. All right, and there's the file was created for us. So there's a MATLAB file. And essentially you'll see the construction of an overall solution. And it's called a function, but essentially this will behave as a script. And so I'll prove that to you now just by hitting the run button. And what we're going to watch is the live calculation taking place on MATLAB. And we'll see that it's finished. It put all the data into this thing called mg4bar.1, which we show right there. Okay. And it tells us, hey, if you want to see what it looks like, just run these commands right here. And so it loads in that data and assigns essentially um, the arrays to something called sum name. I'm going to just hit evaluate, and it'll essentially plot out the results, right? And again, I'm pretty familiar with this mechanism, and we probably have shown this a couple of times already in previous videos, but it's 4-bar linkage that's kind of lined up against gravity, and it is an equilibrium, but an unstable one. And so sooner or later, gravity acts, it tips, and it goes through a rotation. And since it's very close to equilibrium, well, I guess you'd still call it an equilibrium, but it's a very unstable one. It tends to dwell, all right? And that's what I'm seeing right here. And all I want to really just, again, is make the point that this is consistent with my understanding of what this mechanism will do, mostly through the runs that I did with the Simulink models that were created. Okay, now there's a few things to kind of get into, all right, that I think are pretty important. Is that this is a script, and it's not exactly um, it's not exactly kind of optimized yet for everything I wanted to do. All right, and I do want to bring your attention to a few things. All right, that this model is run. Well, I'll say that I want to say this, that we know what a 4-bar linkage is, and we can certainly, kind of run this model. And we may recognize that there are 4 joints, 2 connections to the ground, and then 2 that kind of connect the links. And that we begin to recognize pretty early that each of those joints, are defined by an angle. Maybe you want to throw angular velocity in there too. But 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 where there are 4 joints that might imply 4 degrees of freedom, because there is a physical constraint, where the linkage ultimately connects back onto itself, because both the motor right there and this final connection both connect to that same ground, that there essentially is a loop. And that loop constraint itself will reduce these 4 degrees of freedom down to 1. Okay. And while we're on the topic, we can kind of point out that, well, it seemed kind of strange that we keep on calling this a 4-bar linkage when there are really only just 3 links. Well, the 4th link, of course, that will be the ground connection, so the space between those 2 connections. So anyways, what I wanted to kind of get at is the solution that we came up with here is something that's going to tell us the second derivative on 3 of the joints. Okay, now the 4th one's missing, and it's a little bit hard to explain, but it's essentially buried inside the loop constraint. But what I wanted to say is it truly is a 1 degree of freedom problem, and that simply means that this whole kind of description of it mathematically that's facilitated by this fairly elaborate array structure defined as Z is going to capture that kind of, I'll say, dependency. And the dependency is that the motor angle is independent. All 3 of the other ones, their angle will be dependent upon what the motor angle will be. And I'll simply say that dependency for these additional things that are being calculated for us is constrained properly by those equations. And so, but what I want to kind of get at is that I don't want to do additional numerical integration on these 2 other variables. And I also am not even crazy about the fact that the system of equations is actually a fair bit bigger. It's about certainly at least 96 elements and therefore lines of description of what the system dynamics might be. Okay, so that's one thing. The other thing is, that in our controller, our feed-forward controller, the job of the system of equations is to calculate the needed torque, right? And here it's somewhat inverted, meaning that we give it torque, and this is going to tell us how it's going to move as described by these second-order derivatives on those 3 variables. So anyways, a lot of mathematics, maybe a lot of stuff that we don't want to be too interested in, and therefore, but certainly the numerical advantage of reducing this to something that's even more efficient in calculation, I think there's really good reasons to do it. So what I want to do now is really just kind of move in the direction of converting this into what we need. And so here we'll kind of get a little bit into the operation of, of how all this works. So let's go ahead and save this, save as. And so instead of being FD, I think I'll just call it ID for inverse dynamics. So not forward dynamics, but inverse dynamics. And so, so anyways, let's kind of get into a few things. All right. And I think I'll begin before we even touch ID, the idea of the loop constraint itself, right? And that the loop's right here. And again, it detected it based on the geometry as defined inside SimWise. And it uses this special notation that the variable itself, loop one, has the little angle bracket on it to indicate that it is a vector. And it's a vector that by definition, it's a loop that goes all the way around back to its very beginning, should be equal to 0. And as we take dot products for both x and y directions, we just set up two scalar equations that will be set to 0. Okay, and you'll see the solve command as used right now ended up essentially solving a system of equations that was, it's a little hard to kind of get in and justify that there are three that represent kind of the dynamics and two that represent the constraint of the loop. But what I want to get down to is the fact that instead of solving for 5 things, all I really want to solve for is 1. And so you'll see that the solve command will get reset up with this. And so I'm going to copy this, or actually let's even cut it, and let's paste it right here, and let's comment that out. Okay, so there's our 1 degree of freedom, which will be the motor. Okay, now this is one of the things I brought attention to in the previous video, is this brilliant thing called solve set input DT. And I think it's kind of an awkward name still, but it certainly is named what it actually does. And it really kind of gets into this idea that a dynamic system model really has, I want to say this in a way that I properly define what I mean by initial condition. And again, it might just require another video to truly get into this. But there's this idea that that the linkage is not just the lengths of each of these links, and maybe this is the best way to say it. Okay, that this initial configuration where it's kind of kind of got this nice orthogonality. Well, that the same length links. And so the way I'm going to do this right now is to split this up. I want to keep this guy frozen because I want to make a point that the dependency of the angles depends on how it is initially configured, right? And so with this guy split, it means that I can use this move tool and I can drag that down like that, okay? And I can use that same move tool to drag this guy like that. And they're pretty close. And I think if I do this thing called join, I think it'll bring them, oops, not create, but join. And assemble just says move the bodies to accommodate that configuration. Oh. Now, I like that I did this, but I now need to explain what that error was. Okay, so I anchored this so that it could no longer move. But I wanted to, again, maintain its angle and show that there are two kind of orientations that can be facilitated by the lengths of these bodies and the joints that we've imposed, and that this is the second configuration. Now, if I hit run, you'll see that it moves like that. All right, so same bodies, same joints, but completely different mechanism, right? And anyways, now getting back to what we're doing with solve set input dt. And again, there's some, really, I'll say, thoughtful effort that was put in to choose initializations that represented that original configuration. And so basically, this is going to initialize everything as well as eliminate these variables from showing up quite as fully in the calculation. And so that's the idea of solve set input dt. And it means that an initialization needs to be provided right now for what the motor's doing and what the motor's angular velocity is doing. Okay, and so we're getting really close to kind of having this work. And so the last thing I need to get into is kind of the definition of joints. All right, and so prior to joints, we've already gone through the definitions of what the bodies are, rigid bodies A, B, and C. These essentially are objects that do have methods, and it's through that objects methods that we do things like we set the mass and the inertia. We also start attaching coordinate frames, and it's finally through these coordinate frames that we've set up, and we'll see stuff like ACS1, it's the first coordinate system on the body A that we set up some constraints on the frames for the creation of the joints. Okay, now what I need to kind of get into is there's this idea of, well, okay, those joints are real, they are moving, that they are facilitating connection between parts, but they're not really degrees of freedom anymore. And that our true degree of freedom will be the motor angle. And that we're setting this up with our first joint, which we are calling the motor, right? And here's where I need to get to, okay, is that there's a variable for the motor, there's a variable for the torque that we're going to deliver to that motor, but there's also a designation that's made here that's took me a while to understand that that's what this really was. And it's a Kane type of term, and it's called setting the generalized speed, right? And so that idea that we're reducing the degrees of freedom means that ultimately we're no longer allowing the other joints to be defined as degrees of freedom. And so for the most part, I think I got this. There's a chance I missed something, but essentially by the time we get to here, we've figured out the kinematics. Oh, actually, you'll see in the way that the file itself is written, it gives you the instruction, says, hey, if you're going to use solve set input dt, also comment out these next two lines. Okay, and so with that, then this loop is defined in terms of vectors. We get the dot products, we get these equations, which then are used to reduce the overall system equations from 3 down to 1. All right, and again, it's all fairly technical, and maybe I will create additional videos where we really get into the details of this. But at this point, it's all kinematics and motion description. We put in a gravity definition, and it's only once we create our system of equations for mechanical dynamics, which we're going to call Kane's equations, that we really bring F into it. And it's here that we take our very carefully defined, I'll say structure that will dictate the kinematics available, but we set that, which I'd say implies A, the acceleration of any point on any one of these bodies. But it's only when we get the system of equations we start attaching it to the forces that drive the system. And so I think I'll go with this. At this point, we've already initialized everything that actually, we're going to keep those numerical integration settings maybe just for a little bit longer. Okay. Actually, you know what? I think that that'll be overly redundant. And here's where I'm going to go with this, right? And so instead of solving the ordinary differential equation, all I want really is going to be, give me the code that represents this system, right? And so I'm going to type in this code algebraic, which will solve Kane's equations, and it's going to solve it instead of for QRZ motor, it's going to solve it for the torque. Okay, and so that means we're going to give it the motion, and it's going to solve it for the torque. All right, and so let's put that in there, and I think that's it. Yeah, absolutely, I could have made a mistake, and if I did, I might re-record this video. So let's copy that. Oh, actually, I'm going to do one more thing. Okay, and I'm going to add ID to the name that we're going to give it. And in a second, I think I will even do a little bit to really kind of point out how critical the dot M there is, but that's the direction that essentially tells it to solve for the or to express this system of equations in MATLAB code. So let's see how we do. So let's copy, and so we'll clear everything that's in there right now. All right, so we're back to step one, and let's run it. Okay, I did mess up. And I'm gonna try one more thing. I don't think oh, yeah, we're not solving for that. And let's try one more time. And if I mess this up, I probably will re-record the video. So let's clear it again. Did not initialize, which probably should, but otherwise got it to work this time, right? And all I'm gonna do now is just kind of finish by showing you the new MATLAB function that was created. And this is real close to what we put in, and you'll see one of the things is no longer do we have 98, I'll say the algebraic calculations for this whole Z array, it's down to 63. So there's absolutely been this reduction. And I guess we see this probably near the top, that no longer are we solving or employing the second derivatives on anything other than the motor itself. So um, anyways, I think there will be additional videos where we're going to really bring in MotionGenesis. I'd say the next one will be a video where we really get a lot more into the depth of proving that there is an equivalence in the calculation provided by Simscape multibody and the you know, that provided by the equations in motion generated by MotionGenesis. And as I say, these two tools are very complementary to each other, and the idea that the same SimWise model. Again, I got it in this alternative configuration. Actually, let's go back to there. That the same SimWise model being the mechanical description that is the basis for both the creation of the Simscape multibody expression of the mechanics as well as the MotionGenesis. That's a key to why all this works so well together. So anyways, thank you very much.